Now that we've gone over how to write the Ka, the Kb, and the Kw equilibrium expressions, we need to discuss their values a little further. So if we have Ka, remember this will describe the reaction of Ha, which is an acid, reacting with water to form hydronium and the conjugate base. So Ka for this reaction will be products over reactants. So it will be H3O plus times A minus over Ha. So what does this mean in terms of the values we can get for Ka? Well, as we can see, the greater the numerator, the greater that Ka will be. So what does this mean for the strength of this acid? Well, the stronger that this acid is, meaning the more likely it is to donate its hydrogen, the more products we will see. So if this Ha donates a lot of its hydrogens, we will see a lot of products form, and therefore in our K expression, Ka will get bigger. So the larger the Ka, the stronger the acid. So if we think about Kb, the base reacting in water, remember our base is going to take a hydrogen from water. Water will act as an acid here. This will form Ha and OH minus, which is hydroxide. Right. So we write our Kb expression for this. This is going to be equal to Ha times OH minus over A minus. So what we can see is the stronger this base, the more it will accept a hydrogen from water and produce our products, which we can see right here. And the more products we make, the bigger our numerator and the greater Kb will be. So in the same way, the larger Ka, the stronger the acid, the larger the Kb, the stronger base. And this makes sense. Basically, for an acid and a base, the more likely it is to react with water to produce products, the more likely it wants to react as the acid or the base, making it a stronger acid or a base, the more products we are going to see, and that numerator for Ka or Kb will be bigger. So the last one, which is Kw, move this up, Kw, H2O plus H2O this is going to be H3O plus OH minus. Kw for this reaction is H3O and OH minus. Now, for Kw, it's a little bit different because we are not changing our acid or base like we are in these other two reactions. So we can't really say it's a larger value for a stronger acid or base. The reactants are always the same. What this does depend on is temperature. So at 25 degrees Celsius, which is the standard temperature, which is room temperature, Kw is equal to 1 times 10 to the negative 14 molar squared. So when we multiply the concentration of H3O plus by OH minus at 25 degrees Celsius, the Kw for this reaction will be 1 times 10 to the negative 14. So as we can see, for these three equilibrium expressions, based on whether we have a stronger acid or a stronger base, we will see a larger Ka or Kb value. And then for the Kw reaction, we will see at 25 degrees Celsius, Kw will be equal to 1 times 10 to the negative 14. Now, continuing our discussion, if we have an acid, say we have, this is acetic acid. So if we were to take acetic acid and we were to put it in water, the acid will give away this hydrogen right here. Water will act as a base. This will become CH3COO minus. It lost its hydrogen, and water will become hydronium. So the Ka for this reaction is going to be equal to CH3COO minus times H3O. Remember to put our over CH3COOH. So whatever our Ka value comes out to be for acetic acid, now I'm going to make up a number for it because the real numbers are not important. So say this was 1 times 10 to the negative 6. That is what Ka is equal to for acetic acid. So what if instead of reacting acetic acid in water, we react acetate in water? So you don't need to memorize the names of all these things, but this is acetate. So what if instead of this reaction, we run this reaction? CH3COO minus. We react this with water. Now water will act as our acid to give a proton to acetate. This will be CH3COOH and hydroxide. Now, when we write our expression for Kb now, this is a base reacting in water. This is going to be CH3COOH times OH minus over so if we do not have the value for Kb, we can use Ka and Kw to solve for Kb. So one really important equation to know is that Kw is always equal to Ka times Kb. So if we are at 25 degrees Celsius, we know that Kw is equal to 1 times 10 to the negative 14. We saw that on this page right here. If it is not equal to 25 degrees Celsius, we cannot call Kw 1 times 10 to the negative 14. We would have to be given that new K value. So you do not need to memorize a bunch of Kw values for different temperatures, but 25 degrees Celsius, it is really important to know that Kw equals 1 times 10 to the negative 14. So as long as we were at 25, we can say that 1 times 10 to the negative 14 molar squared equals Ka, which is equal to 1 times 10 to the negative 6. And if we want to solve for Kb, all we need to do is divide, and Kb will be equal to 1 times 10 to the negative 8 molar. So, as we can see, knowing Ka, Kb, and Kw is really important. Writing the expressions for them is really important. The larger your Ka, the stronger your acid. The larger the Kb, the stronger your base. And Kw at 25 will be 1 times 10 to the negative 14. And when we have an acid or a base, all we need to do is just know the Ka or the Kb, and we need to be at 25 degrees Celsius, and we can solve for our missing variable if we need to find Ka or Kb.